Students, we are back with another lesson. In this lesson, we'll discuss compound microscope. So, in the topic compound microscope, using the help of ray diagram, we will explain the working of the compound microscope, and after this, we will write an expression for its magnifying power. Right? So, your compound microscope, okay, it usually consists or it is composed of two convex lens. The first convex lens is your objective. This convex lens has a short focal length f suffix capital O. O stands for your objective and having a small aperture. Small aperture means a thin convex lens. Fine. So let us consider a principal axis. In this principal axis, consider you have a convex lens of short focal length and thin aperture. Fine. So this is your objective. Fine. So let me write down below this one. Fine. This is your objective. Now consider an object AB. Fine. This is your object AB. Let me write down object AB. Fine. This object AB is placed beyond the focal length of the objective. Okay. So for the focal length, you can consider this point as the focal or principal focus of the objective. Fine. So let me write down this one F suffix O. Fine. If this is F suffix O, then this distance represents the focal length of the objective. Fine. And your object AB is placed beyond the focal length. Fine. Fine. Now consider a ray starting from this point A. It moves parallel to the principal axis and strikes the surface at this point. Fine. This is your first ray. Now it is moving parallel to the principal axis. Fine. This black line is your principal axis. Now this ray after refraction will pass through the second focus. Fine, like this. Let me draw this one. Fine. So after refraction, it passes through your second focus of this objective. Fine. So this is your first ray. Fine. And always draw the arrows. Fine. Always show in which direction your light is moving. Fine. Now consider a second ray. The second ray, let us consider it passes through the optical center. Fine. Optical center of this objective. Okay, so let us look at this line. Wait. Okay, so I've made this little bit bigger. Okay, so this is your second ray which passes through the optical center and it passes undeviated. Fine. Now at this intersection point, a image of this object AB will be formed. Let this object be A dash B dash. Fine. it is in the downward direction, and this is your A dash and your B dash. Fine. So your objective forms the image of the object AB as A dash and B dash. Fine. Fine. So let U naught be the object distance for your objective, and VO, okay, VO be the image distance for the image A dash B dash. Fine. Now, so this was your objective. The next convex lens is your eyepiece. This convex lens has a larger focal length. Okay, larger focal length in the sense that your, I can say, FE, okay, I can write your focal length of eyepiece is greater than the focal length of the objective. Fine. Let me write this. Okay. So your focal length of the eyepiece is greater than your focal length of the objective, and your eyepiece has a larger aperture, means it is thicker. Fine. So let's draw a eyepiece now. Fine. Now consider a eyepiece. Okay, this eyepiece is thicker as compared to your objective, and this eyepiece has a larger focal length as compared to your objective. Fine. Now, for this eyepiece, this object image A dash B dash will act as a object. Okay, the image A dash B dash of the object AB formed by your objective will act as a object for eyepiece. Fine. Now for this, consider a ray which starts to move from this point A dash and it moves towards this eyepiece. Fine. In this direction. Okay, so this is your ray. Okay, and one more important thing. Okay, please note that the distance between the eyepiece and the objective is arranged in such a manner so that your image, this A dash B dash, okay, this A dash B dash is formed within the focal length of this objective. Okay, if the focal length of the objective is somewhere here, fine. So therefore this objective and your eyepiece should be arranged such that this image for your objective, okay, and image for the eyepiece eyepiece, okay, should always be formed between the focal length of the eyepiece. Fine. So if you consider this point as the focal length or your principal focus for your eyepiece, fine. Fine. If this represents the first focal length, okay, sorry, in this case this is your second focal length. Okay, this length is your second focal length, and the rays where they converge after refraction is your first focal length. Okay, this length is your first focal length. Okay, and this is your second focal length. Now if you look, the image is formed between the focal length. Fine. Now coming back, this AB, A dash, B dash acting as object. A ray starting from here goes and strikes the lens at this point. Now after refraction, what will happen? This ray will propagate along FE. Fine. Can you see? A ray moving parallel to the principal axis after refraction moves along your FE. Fine. So this is the ray. Now another ray, okay, it moves along the center in this direction. Fine. Fine. So look, it is moving in this direction. Now, if you see, are the rays intersecting? No. Unlike in your first case, the rays, okay, the refracted rays are intersecting. Okay, can you see the rays, this one, the first one, and your second rays are intersecting to form a image. So if the rays are intersecting, then what kind of image will it be? It will be a real image, and since it is upside down, it will be a inverted image. But for your eyepiece, are the rays intersecting? No. Then in that case, what happens? You have to extend this in the backward direction. Fine. So let us first extend this one and this one. Fine. So let us extend this ray in the backward direction. This one. Fine. Now, in similar manner, let us extend the second ray in the backwards direction. Fine. Fine. So, if we extend this in the backward direction, let us consider this is your imaginary ray. Fine. Now, what will happen is that your eyepiece, this eyepiece will form a virtual image. Okay, a virtual image will be formed at this point. Fine. So, a virtual image will be formed by your objective, and this virtual image is also inverted. Fine. So let us denote this virtual image as A double dash and B double dash. Fine. So to summarize, your object, this object forms a real and inverted image A double dash B dash. This inverted image acts as an object for your objective, and it forms a virtual image A double dash B dash. Fine. So I can say the object AB forms a final image A double dash B dash. Fine. So for your eyepiece, this this distance will be the object distance. Fine. So let me write down this one as object distance. Suppose U denotes the object distance and E stands for your eyepiece. Then this distance represents your object distance. Okay. Now one more thing. When the object is placed between this distance, okay, in that case, this arrangement, the arrangement of your objective and the arrangement of your eyepiece will form the image at the distance of least distance of distinct vision. That means the distance up to which your human eye can see clearly. If the image is formed beyond this distance, then you cannot see the clear image. Okay, so the image or your final image A dash B dash is formed at the least distance of distinct vision, and this distance we will denote with capital D. Fine. Fine. So this is the least distance of distinct vision. So let me write down here. Fine. So